So here we have to interpret a velocity time graph. So here is velocity, how quickly these people are moving in a certain direction. So you can see before you even start, Sam has a constant velocity of 10 meters per second, whereas Joe is not moving. They have zero velocity here. And then you can see that their velocity is increasing, so they're accelerating here, and now they have a constant velocity of 15 meters per second. So they start off slower than Sam, then they accelerate, so they end up with a final velocity greater than Sam's. So this is actually a very easy question if you understand how to apply it, mainly because it gives you the equation here. So it says, how far did Sam travel during these 15 seconds? So this is the whole length of the graph. So we know that they're traveling at 10 meters per second, so that's our velocity, and we know the time is 15 seconds, so it's just 10 times time, which is 150 meters. So that's really quite easy. Now, this is easy, but you might not get this if you don't understand what resultant force is. So at which of these times is the resultant force on Joe bigger than the resultant force on Sam? If you don't understand this word here, resultant force, which means net force, you will completely not understand this question. So to understand resultant force, it just means net force. So if you take one force acting on an object against another one in the opposite direction, how much is left over? So here you can see nothing's left over because 10 cancels out 10, so the resultant force is 0. Here 15 newtons is playing off against 10 newtons, so there'll be a resultant force of 5 newtons in this direction. Now what you really need to know is if the resultant force acting on an object is 0, then it either is moving at a constant speed if it was moving anyway, or if it wasn't moving, it will remain still. This is effectively Newton's first law of motion. An object will remain at constant speed if the resultant force acting on it is 0. If, however, the resultant force is greater than 0, then the object is accelerating. This is the knowledge you have to apply to this question. So which of these times is the resultant force on Joe bigger than the resultant force on Sam? In other words, if you think about it, Sam has a resultant force of 0. How do we know this? Because they're moving at a constant speed. And as we know, constant speed means the forces acting on are balanced. So the resultant force is always 0 for Sam. For Joe, if we look, not moving here, so still, so the resultant force is 0 here. Here they're moving at a constant speed, so again, resultant force is 0, but here they're accelerating, their velocity is increasing, so the resultant force is greater than 0. So the only point in this journey where Joe has a resultant force greater than Sam is over this stretch here, because Sam's is 0 all the way through, and this is the only point where Joe's isn't 0. So the next part is just reading a graph. So 3 seconds, nope, that would be here where they're not moving. Then 7 seconds, well, that's on the rising part of the graph. So yes, it would be 7 seconds. That's the answer. Next is just a matter of reading a graph. So how many seconds was Joe accelerating for? So we go from 10 to 5, so that's 5 seconds, then another second here. To work this out, you just count the number of squares from this point to this point, so there's 25 squares here, and divide by 5, and that'll tell you how many of these equal a second. So that's 5 little squares equal 1 second. Then the final part of this question, it says calculate Joe's acceleration during this time. So acceleration is a change in velocity over time. So change in velocity is basically from here to here, so we read off the graph, so 0 to 15. And the time we worked out in our last question was 6, giving you an answer of 2.5 meters per second squared, because that's the unit of acceleration. That doesn't mean you have to square the answer. That's just the unit. Like centimeters squared is the unit for area, and centimeter cubed is the unit for volume. Don't cube or square those answers, so you don't square this one. I only say that because I've seen a lot of students do that, so please avoid that. Final question, very loaded, lots of information, time to get your pen out to underline key ideas in the question. A teacher takes a group of students onto a sports field to measure the speed of sound in air. So they're measuring the speed of sound. The teacher fires a starting pistol, so we've got a starting pistol being fired, which produces a bang, a loud bang, and a flash of light at the same time. The students take measurements. Describe how the measurements are made. So in other words, what equipment do you need to take those measurements? and used as well. So it's two parts of this question. What equipment do you need? How are you going to use it to determine the speed of sound in air? You may draw a label diagram to help you with your answer. So I'm a big fan of drawing diagrams on my exam papers because it helps me visualize what's going on. So you've got your students over here, and then at some distance away, I've put 300 meters, you've got a teacher firing a gun. Now, it's important to understand this is not for safety. The reason why they are quite a distance back, around 300 meters back, is because sound travels at 330 meters per second. So in other words, in 1 second it travels 330 meters. So if you shot it from here, you'd hear the sound instantly and you'd see the bang or the flash instantly, and you wouldn't be able to see the delay between them. But if you move further back, then it takes time for sound to travel to your ears, whereas the flash traveling much faster, because light travels at 300 million meters per second, roughly. That will basically arrive at your eyes instantly, but the sound will travel. So by moving back, you get a delay between these two events. This is why I've drawn the flash arriving instantly and the sound not instant. So remember, we're back to that old equation of distance divided by time equals speed. So what we have to do is describe how we will measure the distance and what distance we will measure, how we will measure time and what will we be timing, and how will we determine the speed of sound. That's what our answer must contain. So, firstly, we need a large distance between the pistol and the timer. We've just said that. About 300 meters. You measure the distance using a trundle wheel. This is a terrible drawing of a trundle wheel. I don't know if you've seen one, but they're basically a round disc that clicks every time it travels a meter. You could also use GPS or something like that on your mobile phones these days. With modern technology, you can include that in your answer. Now, that's how we use the equipment to measure distance, so we're obeying every part of the question. Now about time. Start the stopwatch when you see the flash, and then stop it when you hear the bang. So once again, we've mentioned the equipment we're using and how we're going to use it. Then you divide distance by time to determine the speed of sound. So now we're basically showing how we calculate the speed of sound. And finally, we repeat to increase reliability. So remember, when you get one result, you don't know if it's a reliable result. You don't know if you just got it by chance. So you repeat it a number of times to make sure that it wasn't just down to chance. Just remember, the key idea here is to address every part of the question. That's how you get your marks in these 6-mark questions. And every 6-mark question you get right, you pretty much go up a grade.